Hello, my name is Theodore Alishay, and today I will be discussing Lab 5, Magnetic Braking with Faraday. Firstly, the purpose of this lab was to explore the interaction between a falling magnet and a tube of aluminum foil, as well as model the magnet-tube interaction computationally, and lastly, compare the computational predictions with the observed data. The fundamental physical principles that we used in this lab were the induced non-Coulombic EMF, which are determined through Faraday's law and Lenz's law, the Biot-Savart law, and Newton's third law. The main result was that the average time for the bar magnet to fall was 0.92 seconds, which is slower than if it were falling through free space. The computational model had the north side of the magnet pointing up, and I determined that the red rings corresponded to a counterclockwise current, while the blue rings corresponded to a clockwise current. When the magnet was flipped so that the south side was pointing up, the system dynamics remained the same. In the computational model, I had a total time in the tube of about 5 seconds, which was much more than in the real-life model. My procedure included a system of the bar magnet, the surroundings including the aluminum tube, and the initial conditions at t equals 0 were that the velocity of the bar magnet was 0. I dropped the bar magnet through the tube 5 times in order to determine the average time spent in the tube. My glow script model included creating the tube as well as a graph to show the velocity versus time. This also created the tube, and then I wrote out the properties of the magnet, including the mass and the magnetic dipole moment, as well as its position. Then I had to define 2 functions, one of which determined the magnetic field, and one of which calculated the change in flux. The last part of my code included actually moving the bar magnet through the tube. And here's a video of the model. My conclusions. So in order to determine the direction of the current in the red and blue rings, the red rings were above the bar magnet and the blue rings were below. And I basically used the Faraday's law and Lenz's law in order to find the direction of the current. So when north is up, the magnetic dipole moment is in the positive y direction, but the magnet is moving in the negative y direction. So that means that the rings above the magnet have a counterclockwise current. If the magnet direction were to change, the drift velocity wouldn't change and the magnitude of the induced EMF wouldn't change, but the rings underneath the magnet would now have a counterclockwise current instead of a clockwise current. In order to improve the accuracy of the model, I could have remeasured the magnetic dipole moment of the bar magnet and also modeled the tube as a continuous tube rather than several rings. The shape of the velocity versus time plot shows us that when velocity is constant, the bar magnet reaches drift velocity and the gravitational and magnetic forces are equal and opposite. Some possible sources of error were that I determined the timing of how long the bar magnet was in the tube from the video, but there were a small number of frames per second, so it might not have been very exact. And I used the calculated bar magnetic dipole moment from lab 3, which could have been erroneous. If the resistivity of the conductor were very close to 0, then the total time spent in the tube would increase to a very high value, basically infinity, and the induced current in the tube would also basically increase to infinity. If holes or slots were cut into the tube, then no current would be induced in the rings because of the hole, and the magnet would behave as if it were falling through free space.